Well, good morning, everyone. It's a real pleasure, and I mean real pleasure, to introduce Dr. Gu Jin today. And Dr. Jin is an associate professor of geophysics, and he is a co-director of the Reservoir Characterization Project at Colorado School of Mines. His research interests focus on applications of distributed fiber optic sensing, and this is in both geoscience and in engineering, as well as seismic imaging and machine learning techniques. Dr. Jin has more than 70 publications and 12 granted patents. He received the ARMA Case Study Award in 2025. He delivered the AAPG SEG Distinguished Lecture in 2024, and he received the Best Paper Award at ERTEC in 2023-2024. Now, before joining Colorado School of Mines, Gu worked for 5 years as a research geophysicist at ConocoPhillips. He earned his PhD in geophysics from Columbia University, and he holds dual BS degrees in geophysics and in computer science from Peking University. So a real pleasure to introduce Dr. Gu Jin.
Right. Thank you very much for the introduction, and really appreciate this opportunity to, present a case study that I enjoy a lot, at least, in this year and last year, that we're able to put together multiple diagnosis tools and find this really interesting geological phenomenon that we're doing hydraulic fracturing. Then we're really questioning like how frequently this thing can happen at different locations, and also what's its impact on the hydraulic fracture stimulation. So you can tell from the title that this is really something happened in the West Texas, also in Chang Eagle Ford. But at the end, of also showcase this is really I would call it a global problem because we also see a very similar phenomenon in China too. Before I start, I also want to honor all my co-authors, and you can see this is a very big joint collaboration, from the universities, national labs, as well as private sector service companies. So the outline of this is pretty easy. So I'll start with some introduction and set up the scene. And then we'll talk about crosswell string measurement. Right now it's more like a routine measurement or regular diagnosis, but we find some irregular signal in this regular diagnosis. Then I will talk about how we integrate, I will talk about the uncertainty of a single measurement and how we are able to integrate the multiple measurement, multiple physics measurement together to narrow down the possible hypothesis, right? Then we'll lead some discussion and conclusion. Okay, so I'll set up the scene with something very, very basic. I think for this community, this is basically something that, is so fundamental that you always believe it, right? So it's like is the fundamental level of how we operate, some assumptions and how we operate hydraulic fractures. So if you think about like how we do the hydraulic fracture nowadays, we drill a well along the minimum stress direction, and then we start to break the well bore into many stages, and we hydraulic fracture stage after stage, perf after perf. And the hope or the belief at that point is that the tensor fracture we grow will be perpendicular to the minimum stress direction, and because that's the least resistant that the fracture can grow. And also because our wellbore is along the minimum stress direction, so the hydraulic fracture will basically be, perpendicular to my wellbore path and parallel to each other. So, we put in 100 perforations along the wellbore, divided into 20 stages. We kind of hope that we grow 100 hydraulic fractures that are all parallel to each other, right? So this is, is a good hypothesis, and but it's underlying that first, it's this, is underlying by some geological assumptions, right? So first, the minimum stress is horizontal. No one really do the at least regular hydraulic fracture, unconventional development in a thrust fault regime, right? Because your hydraulic fracture will be parallel, horizontal in that case. And also we assume that the formations are homogeneous and without the, strong influence of natural fractures. So that's a big assumption, but we can tell how good it is. So this is the assumption we made, and but more importantly, we want to understand that how real these assumptions are, right? So, or how valid this is. So we need to characterize the hydraulic fracture. We need to know what the hydraulic fracture actually look like in the subsurface. So traditionally, we have been using microseismic, which is a great tool. We still use it. I will demonstrate actually how it can be really helpful in this case as well. But microseismic, when we use microseismic to characterize hydraulic fractures, there is a big uncertainty associated with that because no matter how good your acquisition parameters are, your velocity models are, the uncertainty of the microseismic event location can still be, you can argue about that, but in my opinion, about 30 to 50 meters, right? Some people can say you can push it to 10 meters, maybe. So, but there's still big uncertainty associated with that. And also the relation between microseismic event and hydraulic fracture can also be a little bit unclear because we know the hydraulic fracture is a tensor fracture, but most of the microseismic event we observe are shear fracture. So what's the relationship between the two, right? But in general speaking, we believe that where we see the microseismic event during the hydraulic fracture operation, those are where those represent somehow the geometry of hydraulic fractures. But you still have this ambiguity of the location uncertainty. For example, in this really interesting example that you can see, this is the microseismic event happening with one stage. On both sides, you see is does event appear perpendicular to the borehole, which is great. But there's no way we can see the individual fractures. If you push to the limit, you will find you can actually get many possible models that how the fractures are growing or looks like just based on the microseismic event. So we need something more precise. We need something with a higher resolution can really tell us about individual hydraulic fractures, right? So to do that, we have to rely on a more recent development of the technology, which is distributed fiber optic sensing. So, for people who doesn't quite know how distributed fiber optic sensing, is just 2 slides of a very short introduction. So basically, we're using fiber, which is the same fiber you use for your internet, right? So when you choose your internet plan, you can always see there's some fiber options there because most of the internet data are transported by the fiber. The reason that you can see me giving this presentation right now is because the data is being transferred through the fiber network even at this point. But if we repurpose those fibers, instead of using it for transportation, we can also use it for sensing purposes. The idea here is if we connect one of the fiber with a sensing measurement instrument called the interrogator, and this interrogator will send the laser pulses that will travel down the fiber, and any part of the fiber, because there are built-in heterogeneities and defect in there, any part of the fiber will be able to reflect a little bit or backscatter a little bit of the laser energy injected into the fiber backwards to the interrogator. So the interrogator, actually, you can see that the interrogator is sending out the pulse traveling along the fiber, and every piece of the fiber reflect a little bit energy back towards the interrogator. So the interrogator is almost like a 1D radar. It's basically just measuring, hey, what's going on along this fiber, everywhere along the fiber. And because speed of light is very fast, so every second we can send in 10,000 pulses into the fiber and without having them interference with each other. From this backlight, from the back scatters along the fiber, we're able to measure vibration, strain, and the temperature everywhere, anytime along this fiber. So if you think about the functionality of this system, it looks very much like our human skin or human narrow, or we call it human sensing system, right? Because if I don't really need, I close my eye, if someone pinch my arm, I immediately know where, when, and what magnitude, how hard, someone pinching my arm, right? So this is actually what we see on the fiber. So anywhere along the fiber, at any time, any location along the fiber, we're able to measure, temperature. In this particular case, we're able to measure the strain, whether the fiber is being extended or compressed with a very high spatial and temporal resolution, but also very high measurement sensitivity. We can actually, at this point, the modern instrument can even measure up to nano strain, extension and compression along fiber. So the fiber itself, if you got the chance to see that from your internet setup, the fiber itself is very brittle. It's made by glass, and however, if you protect it really well with a lot of armors, with a very metal casing outside, so you can make the cable with a fiber embed robust, mechanically robust enough so that you are able to safely deploy it along your horizontal well. So now the horizontal well is something we call the instrumented well. And then if you connect the fiber on the surface, one end of fiber on the surface with that interrogator, then all of a sudden along the entire well, anywhere, anytime, you are able to see whether this wellbore or the surrounding formations are being extended or squeezed because we are actually now measure string along the entire wellbore. This measurement turned out to be extremely useful for hydraulic fracture characterization because when we're creating hydraulic fractures in the subsurface, as shown in this model from Zhishui Zhang in Chevron, published a couple of years ago, so the hydraulic fracture is actually mimicking here. The hydraulic fracture, as it propagates, even just by existence, it actually create a strain field or stress strain field surrounding it, characterized by the compression strain on both sides of the hydraulic fracture, usually we call it stress shadow, as well as the extensional, we call it the heart-shaped stress head, extensional stress accumulation zone near the tip, where actually promote the fracture to propagate. Right. So this is our natural prediction from the geomechanical model. If you just run the equation. However, if you as you are creating and propagating this hydraulic fracture from your treatment well, if you're placing a fiber-enabled monitor well just near it, then you are able to capture this strain field. I made an animation to help you understand this process, right? So I have a treatment well, and which is, I'm injecting and creating this growing hydraulic fracture that I see on the left. And on the right, I have a monitor well that's measuring the strain perturbation that caused by this hydraulic fracture propagation. So on the right here, this is what we all observe. This is actually what you can see even in real time nowadays, that you see, as the fracture propagate, you start seeing the strain pattern or signal patterns, on the fiber measurement. So the one on the right is sometimes called, if you're not familiar, it's called the waterfall plot, where the vertical axis is always the distance along the monitor well, horizontal axis is always time. And in this presentation, blue color means the fiber is being compressed at that location, and red means the fiber is being extended at that location. So you can see immediately, we'll see a couple of signatures in here that before the fracture hits, we see this heart-shaped signal in here. And then after the fracture intersect this well, we see this very sharp extensional zone that indicated the location where the hydraulic fracture intersect with my fiber instrument monitor well. And because the spatial resolution of the fiber measurement can up to below 1 meters. So that basically means that we are able to pinpoint where the hydraulic fracture intersect my monitor well at a very, very high accuracy, right? So if you don't trust me, on the geomechanical model, so here is actually what we really observe in the field. So this is an open data set you can download from the Hydraulic Fracture Test Set 2 website. And on the right is what we observe in the field. On the left is what the geomechanical model tells us what we should observe in the field. You can see the match are really good. We're able to see the stress shadow on both sides of the hydraulic fractures. We're able to see this heart shape in the beginning. And also very importantly, we can really pinpoint where that hydraulic fracture intersect my monitor well, which we call the fracture heat location, right? So, you have a fiber well, you have fracture heating the fiber well, and you can really know where that fracture intersection points is. This turned out to be a really powerful tool, even this very, very simple diagonals. It turned out to be a really important tool to understand the fracture geometry. Simply because of the really, really high spatial resolution, we're able to identify individual hydraulic fractures. Remember when I talked about the microseismic, at the stage level, we can really see, roughly the fracture are growing in that direction. But now we are able to see individual hydraulic fractures that are propagating, in the subsurface. For example, in this particular stage, we easily identify there are 3 hydraulic fractures, characterized by the extensional signal during the fracking and the blue like compression signal after the pumping stop. So there are 3 hydraulic fractures that intersect my monitor well at these 3 precise locations. And also keep in mind that we're fracking the treatment well stage by stage. That means that we know where those hydraulic fractures initiated. And if we repeat this process and connect the dots between the fracture hit and then the perforation for that particular stage, we can start creating the hydraulic fracture, creating this hydraulic fracture connection map between my treatment well and between my monitor well. So, and then you do that stage after stage and color them by stage or color them by fracture, you find actually our assumption is not bad. So the hydraulic fracture R seems to be parallel with each other, stage after stage, fracture after fracture, and aligned with maximum stress, horizontal stress direction. So at least in this case, our original assumption that the hydraulic fracture are assumption that hydraulic fracture are parallel to each other, perpendicular to the minimum stress direction, it seems to be valid, right? So, but this is just one case. And so when this method propagating, we publish this method and more and more company and people start using it in different basins, we see again and again that our assumptions seem to be valid. So this is a case of an Eagle Ford. You see the fracture are parallel to each other. This is a hydraulic fracture test 2 in the Delaware Basin. Again, you see the very parallel fracture communication between the injector and monitor well. Here's the Montney case, same story. So the fracture are parallel to each other, perpendicular to the minus stress direction. So I would say at this point, the engineers will be very happy. This is basically support their idea of, we don't care about the geology. Let's just frack it in the manufacture mode, which at least in the US, that's most of the operator do. But things going well until it doesn't, right? So here I just want to show you a case study that where fracture doesn't really go as we planned or as we thought. So this is actually also from a DOE, the data also collected through a DOE funded project. It's called ACEFFL Austin Chalk for Field Laboratory. As you can see that, you already tell where this thing happened. So it's happened in the Austin Chalk, but it also happens on the very western side of the Eagle Ford Austin Chalk, so very close to the U.S.-Mexican border, right there. Right, so you can see that the stress. So this is a very famous stress map from the from Zobek's group. You can see that the maximum stress direction is about northeast direction. So you can see that when they drill the well, they drill along the maximum minimum stress direction, right? So which is expected, and also the stress regime is somewhere between. So if you see the color here, it's somewhere between the normal stress and the normal and stress slip, which is also common. You can see that actually most of the assets we're developing right now are under this stress regime. So nothing fancy, nothing abnormal. So the fracture should just grow as we want it along the maximum stress direction. So in this case, that we are both the treatment well and the monitor well are in the lower Austin Chalk, and then they are separated by 1,000 feet. We're simulating this treatment well, and we're monitoring, the crosswell string measurement along this monitor well. So, however, when we start looking at the data, the string signal we observed is very strange. It's actually not quite what we expected in 2 ways, right? So, I will zoom in and I'll explain why it not looks like what we expected. So it's actually the response separated by 2 catalog. And why is this early stage response from stage 3 to stage 6? Stage 1 and 2, the response is actually below the end of the fiber, so we don't really have that measurement. But the early stage is one type. And then on the later stage, we find the signal change very dramatically and very differently. So let me zoom in and tell you how. So in the early stage, okay, so the fracture still look like tensor fracture induced string signal. So nothing weird. But there's one thing that is very abnormal. It's because when we are in the normal case, right? So if I'm fracking a wellbore like 200 feet in here, because fracture are all parallel to each other. Let me go back to this plot. If I'm fracking, a wellbore, let's say this blue stage for 200 feet, I'm expecting the fracture heat at the range of the fracture heat at the monitor well should be around 200 feet. Of course, it can be a little bit larger, it can be a little bit smaller, but because the fracture are all parallel to each other, I'm expecting the fracture heat range should be following or very similar to my stage length in the treatment well. However, in this particular case, it's not. So this black square, which is the spatial extent of this black triangle, is actually, is the projection of the stimulus stage along the magnetic stretching and project into the monitor well. Basically, within this range is where we hope or where we expected to see the fracture hit or fracture intersection with monitor well. And we do see that. For example, in the stage 4, when we start pumping, we see this tensor fracture there just fine. However, you'll see as we start keep pumping and pumping, we're seeing a lot of additional fracture intersection that with a span much longer than my stage length that hitting later in the stage. And we see this repeatedly across all the early stage signal. So this is very strange because we're growing hydraulic fracture within this 200 feet wellbore, but why we're actually creating a fractured zone at the monitor well 1,000 feet away that is 4,400 or 800, 400 to 600 feet wide, right? So are we creating something like a fan-shaped fracture? So that doesn't make sense. So that's abnormal number one. But when we're jumping to the stage of stage 7, and we're seeing that we stop seeing tensor fracture signal anymore. So we see a little bit, for example, we see a little bit here, but they're definitely not as abundant as the early stage. But instead, we're seeing this migrating signal. This is almost like hyperbolic, right? So, keep in mind that this vertical is depth and horizontal is time. So this hyperbolic is almost like something is hitting my well and then propagating, like parallel to my well. So this is also super weird and also characterized by a reversed polarity. So when this signal is migrating to the hill or to up to the hillside, it's shown as a compressional signal. And then when it's migrating to the toe, it's shown as a extension signal. So this is actually very different from the traditional tensor fracture that we observe in the many previous experiment. But what is this? Right? So we did a lot of geomechanical modeling and we found the only way we can duplicate this response is requiring us to have a fracture. It's not necessarily hydraulic fracture, it's a fracture that is propagating parallel to my monitor well. Remember, my well is a horizontal well, so a parallel fracture means I add a horizontal fracture or a vertical fracture, but parallel to the well, okay? And also it has to have a shear motion instead of tensor motion. So basically it means that it need to be a fracture that is not really open up, or the majority of movement is not open up. The majority of movement is actually shearing and propagating. So almost like we're triggering some kind of fault or nasal fracture and make it shear by itself. So, and also again, this is again another argument that the reason that we know it's a shear is because for tensor fracture, the polarity of outgoing or downgoing. So I'm a geophysicist, so sometimes I use a term in seismology. The heel going or toe going migration need to be if it's a tensor fracture, it has to be the same polarity. The reason that we are seeing, in the field that there is a reversed polarity is because you have to add a shear component to create this polarity flip. Okay, so we narrow down the hypothesis. It need to be a fracture parallel to the well, to the monitor well, to the horizontal monitor well, and it has to have a strong shear motion around that. So if you just buy these two assumptions, we have a parallel fracture parallel to the well and it's migrating shear, and then you can really start to history match or mimicking the field string response very, very well, right? So in this case, it's a very simple fracture propagating parallel to the well. From the field data, I know how fast it's propagating at each time step. So I just implement this velocity, and you see that it's actually create a string pattern measurement pattern very, very similar to my observation. So which indicates that my model or my at least my customer model seems to be correct at this point. But the question is, what is this shear plan that is parallel to my monitor well, right? So unfortunately, just within the fiber itself, we just only using the string measurement, we cannot tell because the strings measurement of the fiber is a single component measurement. So we can only measure string. Everybody know that the string is a tensor, right? So I have its rotation. All we can measure is this string tensor projected along my fiber well direction. All I can measure is whether the fiber is being extended or compressed along its axis. So which means that any fracture that is shearing with a certain motion that can be parallel to my well with a 360-degree, all these fractures can create exactly the same string pattern as I capture in the model. So if we narrow it down, if we narrow it down for geological making sense, there are two possibilities. There are actually four possibilities. One is, two of them are bedding plan either above the well or below the well. But the bedding plan, you can see their motion will be shear motion has to be reversed if they are above the well or below the well. It needs to be, if we're on the side view, it will be right hand clockwise rotation if it's above the well, and it'll be counterclockwise rotation is below the well. Both of them can create this string response. But it can also be a strike slip, vertical fault, strike slip, that is growing parallel to my well with a similar fashion, right? So just from the string data, there's no way we can tell. However, the nice thing is now we need to integrate more geophysical measurement into this. The next thing we need to integrate, let's go back to our old trick of microseismic. So besides the location of microseismic, we can also, if you got a good data acquisition setup, you can also get the moment tensor of the microseismic. We know which directions, at least one of the two possibilities in which direction the microseismic are able to are sharing that causing the microseismic event. So first of all, from the catalog, we see strike slip event, vertical strike slip fault. Where we'll talk about this event a little bit later. But they are not, you can see the epicenter alignment are not really parallel to my well. So from microseismic, I don't see any feature that is aligned vertically and parallel to my well. However, I do observe a whole bunch of these half moon events, which are basically, a lot of people call it deep slip event. But in this case, remember, microseismic moment tensor have an ambiguity. We don't really know whether it's a vertical deep slip or is a horizontal, bedding plan slip, right? So in this case, we see actually a lot of these half moon events seem to be along the fiber direction. And one solution is they have a shear fault perpendicular to the well that is along the hydraulic fractures, which in most cases we interpret those events are the deep slip event. However, we argue in this case, this event actually represents a bedding plan slippage. And the even nicer thing is that because remember we have this ambiguity that if this is a bedding plan, the bedding plan above the fiber well and below the fiber well with a different shear direction, they all produce the same string response. However, they represent a very different moment tensor solutions. So from the microseismic, we can actually tell which one is this, whether this bedding plan is above my monitor well or is below my monitor well. So by integrating this, you see on this is a map view. So we're looking at the lower hemisphere of this beach ball. And on the left side, we're looking at the side view, right? So you probably have to reorientate yourself. We're talking about 3D space, but if you trust me, and so most of this event you see in the lower hemisphere, we have this white with extension towards the heel direction and the compression towards the toe. So that agree with a bedding plan that is below my monitor well, shearing counterclockwise. So basically, this fracture solution come with a beach ball that is agree with my most of my microseismic moment tensor solution. So that's closed loop. So we're now by combining the LFDAS and microseismic moment tensor, now we can really pinpoint that this is a bedding plan that below my monitor well. Then the next question is why, right? Why I have a bedding plan that is shearing below my monitor well when we perform hydraulic fractures? So I basically back the operator, so they agree to share with me the the well log, the type log of the nearby vertical wells. And then they didn't hide all the formations, but they do tell me that this is where my monitor wells are. And below, there are two bentonite layers with a very high gamma ray. And this bentonite layer is about 75 to 100 feet below my monitor well and showing as extremely high clay content. So that's actually could be the reason that why you know, this could be our potential target. It's because high clay content from the lab experiment, high clay content can significantly lower your shear friction coefficient in the shear movement. That means that the formation with a very high clay content, they are very easy to shear, even though they may not orientate at the most favorable shear direction. So actually, we do even see that in on the surface. So this is actually Dr. John's backyard, and if you look for it, so on the in the Utah, we actually have this massive gravity glide. So basically, it's a volcanic activity, but the key thing is that as the formation started tilted, the entire block start to sliding along a high clay content layer because they have it has a lower shear stress and the friction coefficient. So exactly what we see in the subsurface, at this. So because of this bedding plan have a much higher clay content, much lower friction coefficient, this could be the reason that causing the bedding plan slippage. And then if there is a bedding plan slippage, it's actually creating all this, can explain all the phenomena that we observe in the data set. Let's start with the early stage, right? Remember, one of the puzzle of the early stage is that when we're fracking only 200 feet at the wellbore, we actually see a fracture head zone over 400 feet or 600 feet. The reason for that is as you start shearing this bedding plan, and the shear by itself, shear deformation by itself is permeability enhanced motion. So that basically means that we start to create a high permeability zone or layer that is parallel to the wellbore that able to propagate the high treatment pressure into the further distance and along the wellbore. And as it go along the wellbore, it start to create a new hydraulic fractures just along this bedding plan and then hitting my monitor well at a much later stage. So this model even explain that why when we're above this protection zone, this hydraulic fracture arrive much later, simply because the fluid pathway actually go into this bedding plan, propagate along the bedding plan, and then create hydraulic fracture hitting my monitor well. So it takes much longer, so it's arrive much later. You can even see this move out, probably mimicking the move out of this bedding plan movement, right? So this is all good. We can explain it in the beginning, but then why? The question here is why after stage 6, things has changed. So I do not see those tensor fracture anymore. Instead, all I'm seeing is actually they're dominated by this bedding plan shear motion. But also, if you look at this data, more carefully, you find a lot of time this apex of this bedding plan. So where at the mountain well, where those bedding plan initiated, it seems to be have, multiple stage. They will stay at the consistent location, and then they will jump to the next location, stay for a couple of stage, and then jump to the next, jump to the next, jump to the next. So it's not really a continuous thing that we're having a bedding plan that growing at our state. We only see this extended length of the bedding plan growing at a certain location. So that basically means that the reservoir has to have a little bit heterogeneity or some structures that are able to propagate this bedding plan into a further distance. So what are those things, right? What's the magic? What are the geological magic that why the bedding plan always initiated, at least at my fiber well, always initiated at these locations? So that's actually now we need to integrate another geophysical measurement, which is reflection seismic, right? So we need to use seismic imaging to see what are there. So there, instead of traditional, like very expensive reflection active source survey, actually in this case, we'll start using microseismic as the source, as well as a single SOV, a single artificial source, permanent source on the surface to see whether we can track these features. First thing is on the microseismic event, we see this very strange reflector that happen to be at the same time where those at the same location where those apex are, and they show a very strong reflection even before we stimulated that section of the wellbore. So it means that there's a pre-existing features that already exist before we stimulating this. And more importantly, during the stimulation, the productive method install a permanent source term on the surface and keep vibrating and keep shooting energy into the fiber, and also creating a time-lapse seismic measurement. So I won't go into technical details into this, but what we're trying to measure in here is we also find this vertical feature actually they show up even before we stimulate, but we also find that this vertical feature, the reflectivity of this vertical feature increase during the hydraulic fracture process, right? So if you integrate these two together, what we find is those are pre-existing faults and fractures that are vertically exist in the Austin chalk, and then they serve as a hypermobility fracture zones. When the bedding plane intersect with this vertical fault or vertical fractures, the fluid also go into the vertical fracture, opening it up and then creating this time-lapse response, seismic response that are associated with hydraulic fractures, with fluid going in. And more interestingly, these vertical faults or fracture location are highly aligned with this apex location that we identified on the hydraulic fractures. So if you put all this together, one of the potential hypotheses here is in the Austin chalk, we have this abandoned vertical, high conductive vertical fractures that when the bedding plates start intersect with these vertical fractures serve as a pressure conduit that are able to propagate the pressure along it and trigger additional bedding plate shear just along this bedding plate fracture. So where this vertical fault intersect with my mountain well is where those apex locations are, where we separate the upgoing and downgoing waves, not waves, fracture propagation, but also. So these are the vertical fault locations. So that's because the vertical fault doesn't move, vertical fracture doesn't move. So that's why we see multiple stage. They always use the same apex location. They just reactivating the same fault. But also, when I'm presenting this at the Penn State, actually, Dr. Terry Edginger actually told me, you don't have to convince me about vertical fractures exist in the Austin chalk with all these geophysics skills or tricks. So he, pull out his amazing experience. He pull out his computer on the Google Earth and then start zoom in, zoom in, zoom in. And I say, and tell me, so this is the equivalent outcrop in the West Texas, equivalent to the Austin chart. So basically, Austin chart coming up to the surface, this is what you see. And look at these features. On the surface, you see these abundant vertical fractures exist of the chalk all the time. So I was just amazed that we're actually seeing exactly the same thing, in the subsurface, with all these fancy technologies. Well, you can literally just see the same thing at the satellite at the same formation. So this fracture, you can see that this entire thing is actually you create a fracture system very different from what we imagine, right? So, we imagine as a parallel fracture all the time, but instead what we see is this, bedding plane shearing and together with vertical fracture reactivation. So you're saying, okay, this must be so weird. You must hit some like geological weird spot that, creating this phenomenon. But actually, it should happen more common than we thought. Actually, this is the study that won us the ARMA 2014 Case Study Award because we see exactly the same thing in the Sichuan Basin when we're doing hydraulic fracturing. And in that case, we even see a very strong representation of this vertical fault and they are shearing at that location. So, just reiterate a little bit, we also see this hyperbolic curve in the low frequency dust data that we see a reverse polarity going up and down. This is the same as we see in the Austin chart. But in the Sichuan Basin, we also see this very, very strong dipole signal. They persistent at the same location, and they start to create a signal whenever you do the hydraulic fracturing, and they form as a blue-red dipole at the same location. So if you do the hydraulic fracture modeling, find this dipole signal is actually caused by a displaced vertical fault that actually growing downwards or upwards. So depending on whether it's going downward or upwards, you can actually create this polarity flip that we observed in the data. So it turned out in this particular case, the bedding plan is also crossing my monitor well because the monitor well is slightly deepening in this case compared to the bedding plan. It's crossing the monitor well that creating this tensor plus shear response right there. So I won't go into detail. We published the paper on SP Journal last year, but you can use this very simple geological model, a bedding plan with couple vertical fracture reactivation. You can actually get a really nice matchup of the string signal we observe in field. So you can see that this is exactly happening the same thing as we observe in the Austin chart. We are trying to perform hydraulic fracture. We try to create tensor fracture along the maximum stress direction, but what we really get is a shearing bedding plan, and then that bedding plan triggered vertical fault, which are shearing in the Sichuan Basin and in the Austin chart cases may not sharing that much, or at least not sharing during the hydraulic fracture cases. Okay, so that will be my conclusion of the study. I just want to share with you this really fascinating phenomenon that we observe during hydraulic fractures. But I also want to show you a workflow or a interpretation technique that you can see if this data set, if I only have low frequency dust data or crosswell string data, I'll be very confused. I don't know whether it's a bedding plan or it's a vertical fall or strike slip. I don't know that. If I only have microseismic data, I probably interpret this bedding plan shear as a deep plane because those are more commonly interpreted that way. If I only have time-lapse VSP, and I won't even know why this vertical fault or fractures are triggered, during the hydraulic fracture, and what's the process of triggering them. However, if you piece all this information together, combined with geology situation, then you can really come up with a full picture of what's happening, what's the fracture network are doing in this particular process. So yeah, so after that, I can see a lot of chat question in the chat and open for questions. Thank you very much.
Thank you, Dr. Jin. Yes, spectacular case study and great recommendations for a workflow. And as you say, you've got lots of questions. Uh, I don't know whether you want to read them. Maybe I'll read them out just so that
Okay.
we know what they are. And
Yeah, but before we start, I want to recognize the DOE funding to support the data
sorry.
acquisition and also the project team that actually make this happen, and also thank the sponsor of my consultant that partially funding this research. Okay, now I'm actually
No,
let's
sorry
go to the
about that.
questions. Yeah, yeah, no, it's
This is an important slide.
yeah, exactly.
Um, so
So
the first question is
uh,
from Kagan, and he's wondering about any insights on the separation of the shear fracture from the observation well. And I think maybe could it be a
well,
transverse failure along the observation well instead?
oh, that's an interesting comment. And actually, from the string data, I didn't really show that. But from the, let me go back to this. So basically, if you're running the geomechanical model, you can place this fracture at a different depths, distance along your monitor well. So actually, you will see that if you put it further and further away, the spatial expand of the string signal and also the pattern a little bit will change a little bit as well. So the spatial span will change as you're moving this fracture further and further away. So just from the data that how the width of this signal in at the distance in your string data, you can actually tell how far away these fracture planes are shearing plane one. Not very accurately, but you can definitely tell this is not a fracture that is 1 meter away from your monitor wall. It has to be somewhere in this model we did a sensitivity study has to somewhere between 50 to 100 feet, which are synchronized very well with these two potential bentonite layer distance. So yeah, so from that we can really tell it's not actually a near wellbore phenomenon.
The next question is from Giovanni, and he's the first part of his question is, can you infer whether the bedding planes are fully horizontal or are they gently tilted? And I think the second
Mhm.
part of his question is whether or not you speculate there's any significant opening in addition to the shear along the bedding plane fractures.
Mhm. Yeah, excellent question. Unfortunately, we don't have that sensitivity to tell like whether it's just a few. We can tell if it's a 40-degree dipping. However, we can't tell whether it's 10-degree dipping or 5-degree dipping just only from the fiber data itself. It doesn't have that sensitivity. However, in some cases, for example, in the Sichuan Basin case, um, let me go to here. So in this case, we actually identify the location where this bedding plan intersect with my monitor well. So in this case, you can actually tell a little bit that at least from the well path, there are some deeping layers right there. We can tell that from this tensor signal here, but as well as we can see the polarity of this vertical shear are reversed. You see, up here is red blue, below is blue red. You need to have the bedding plan crossing it to change the initiation point of the shear to actually creating this polarity flip. So that's one of the way we can tell, but we cannot directly measure the dipping, unfortunately, in this case. The second question, I received this question so many, each time I present it, I always receive this question, whether you can tell whether there's a tensor component of that. The answer is I cannot. So I probably will get a very extremely similar response if I'm just adding 10% or 20% of tensor movement onto that bedding plan. I probably get exactly the same response. So there may be some tensor. So I don't have the exactly measurement of the vertical stress in this case, although and I only have the treatment pressure at the surface. But even though if I have all the data in the world, you can really calculate what's your treatment pressure at the perforation level, how that compare to the vertical stress to see whether we are able to create a tensor fracture or not. But unfortunately, with the data I have access in this project, I won't be able to tell the difference.
Yeah, the several next questions are from Alexei, and you really caught his attention. Uh,
Yeah, great.
does are you able to tell if the polarity of the shear signal how that compares with the bedding plane dip angle?
Oh yeah. So polarity of the OS. the deep angle. I think I probably need a little bit of clarification of this. So again, we are not that sensitive to the deep. All we know that is actually a shear that is parallel to the direction is a parallel to the well, not perpendicular to the well, because perpendicular well will create a different straight response. And also, having this shear parallel to the well also agree with the microseismic moment tensor, as we see in this case. But to be honest, because of the fiber orientation, actually we're very if this bedding plan have a shear that is perpendicular to the fiber direction, you actually are very insensitive to that motion. So we don't really know the actual rate of the shear motion in this particular case. However, I think that one is better constrained by this microseismic. You see that is actually very parallel to the plan. But again, we don't have a good control on the deeping of the bedding plan, at least from this particular measurement.
Okay. And Alexei's next question is, do you consider it a possibility of long-range pure mode 2 fracturing? And if it is mixed mode, then the friction coefficient of the interface is relatively is not a contributing factor, and that tensile strength and mechanical contrast lead to opening of a specific bedding plane.
I think I may need to understand this a little bit better. Let me see here.
So maybe Alexei, do you want to just unmute and clarify?
Can you hear me?
Yeah.
Yes.
Yes. Mm-hmm.
Yeah, I think the question is you were discussing clay content and low friction coefficient at certain bedding planes based on that gamma ray block. And if it's pure shear, that would be right.
I see what you're saying now. Yeah.
How can you have such a long range just mode to fracture? And we observe in some other places, as well as in your case, very long range communication, which would be very easy in mixed mode because mode 1 would propagate very quickly and far away. But in that case, it doesn't matter what friction coefficient is because we already opened the interface. Right. And it's the question about bedding plane, because once it's in mixed mode, so there is basically no resistance to shearing. And then the question is, do we get shear because of induced stresses, or we get shear because we are sliding on few degrees of bedding plane dip? And that would provide the direction.
Yeah. So, I see why you're asking the deep part. I think the deeping part, remember, this is, I argue with people a lot with this. Personally, I don't believe the principal stress has to be 100% vertical. So there's a chance that principal stress can be slightly tilted from the vertical, and also the bedding may not be 100% vertical. So I don't think, just giving that there's a shear motion in there, I'm pretty sure, 100% sure that the bedding plan does not perfectly perpendicular to the principal stress direction. Otherwise, there shouldn't be shear. I do agree that there could be a tensile component in there. And from the data that we measure, we cannot tell the difference. However, I argue that if we have access to the treatment well, and also, like you mentioned in the chat, if I have SSP data, we can measure we can compare the treatment pressure with the vertical stress. Then we can really tell whether it can support the hypothesis with the tensile. But I do agree that, especially, one thing I didn't get a chance to mention in this talk is that once this bedding plan sheared and opened up, the conductivity of this bedding plan is very, very high. So the permeability is really, really high. It's actually showing a communication of the current stage of all the previous stage tensile fractures through this bedding plan. So in that case, after I wrote the paper, I look into the literature a little bit more. At least from the lab experiment, it's very difficult to justify a shear motion can increase the permeability that much, just especially through a clay-rich layer, right? So in that case, I think I would support that. Probably will support there will be tensile and the mixed mode fracture opening. I do agree with you. That I can help to explain the high permeability, post-shear permeability that we observe here. Although I think that hypothesis can be verified with more additional data access, which unfortunately I don't have access for this problem. But thanks for comment, Alexei. That's actually something I'm thinking a lot recently.
We'll give Alexei one last question, and he's wondering was there any casing deformation observed in the monitoring well at the location of the apex?
Especially this is recorded, I cannot comment on that. Give me a call and I will tell you secretly.
Okay, that's a very politically correct answer.
Yes.
So, Jian Chu, let's see. Would vertical fracture parallel to the monitoring well show similar signature on fiber as a bedding plane slippage?
Excellent question. And so with a strong shear motion, because it will show very different signature in string, because a bedding plane will migrate along the fiber, while the vertical fold will stay in the same cross-section area and shear. So actually the Sichuan basin is the best example in this case, that you see this migrating signal that have a different polarity, going up and down. These are the bedding plane migrating signal. And where you see this, where you see this blue red dipole, they are persistent at the same location over time. And these are the vertical fault sharing signal. So you are able to see both in the fiber data, and you can tell the difference by how they look so differently in your measurement. I hope that answered your question.
Now, Pat McClellan, can you provide a little clarification on the magnitude of the in situ stresses?
Yeah, I can't. Actually, if you read, because this is a DOE report, DOE funded project, and if you read this DOE report, which is public information, they have the vertical stress plot against depths, but the scale of that vertical stress is hidden from the report, and clearly, the operator is a little bit protective on this type of information in this project, unfortunately.
Issue, well, maybe in the interest of time, we got to move ahead. Why are and Vikram, why are only low frequency components considered for fracture characterization?
That's an interesting question. Actually, we're not only that's actually measuring string rate in full frequency band. In the low frequency band, we're more looking at the creeping and the quasi-static deformation of the fractures, whether it's a tensor fracture or shear fracture. We're seeing this slow motion of the fracture. We're looking at this almost as this very, very slow semi-static changes. But at the same time, same data set, if you look at the high frequency, you won't be able to see this because it will happen too long time. But you are able to use it for microseismic event, and you are able to use it on the seismic method to see the reflection of this fault. So we actually use both frequency band to characterize the hydraulic fracture, but just because the nature of the signal itself, we're using the low frequency band to capture the aseismic deformation and use the high frequency part to capture the seismic response.
Okay, and then the next question, I think it's from Peter. Apologies if I'm mistaken. Did the microseismic dip slip events you used to confirm that the slip was below the well correlate in time and space to the DAS anomalies?
Again, that's an excellent question, and Peter, unfortunately, you probably will see part of this talk again in your talk next month, in coming weeks. But unfortunately, I don't have a direct access to the microseismic event. I have to work with the operator and the collaborator to make this map. I believe they are time and space synchronized, but currently I cannot confirm that. All I have from microseismic is just this particular plot on this. But I think I hope this data will be public pretty soon. So that I think after publication, I will dive more into this and make sure they are synchronized in time and space.
And one last question, and that's from Nicholas. And he enjoyed your talk. And is it possible to get a first order estimate of the magnitude of the shear displacement in the bedding planes?
Excellent question. So we actually did that, especially when we're doing the history matching of this particular event. We also try to, you can see that we also try to match the magnitude as well. So in this case, we got, I remember we got about like a 1 to 2 millimeter deformation over this particular time, so over these 9 hours. However, keep in mind that the fiber, there's always a big debate about what's the coupling factor between the fiber, especially a fiber in the metal tubing surrounded by liquid gel, this particular cable. What's the coupling factor of this one versus the formation, right? Between the fiber and formation. Some surface experiment actually showing the coupling factor can be 708, means that the string measurement we're having on the fiber may be 7 or 8 times smaller than the actual deformation happening in the formation. So if you scale that up, then we're talking about maybe a centimeter level of a deformation over these 8 hours. So at least that gave you a scope, a range that of that.
And then the questions just keep on coming in. Well, one last one to Luis. Any plan?
Yeah, I think Olga also have Igor also have a hands raised up. Yeah, I'm free. I can stay a little bit longer, so it doesn't matter.
We'll keep going.
Yeah.
Luis is
Great
interested.
discussion. Thank you very much.
Any plans to look at performance of wells, production behavior of different frac signatures over time on the fiber?
That's excellent question. And again, I didn't get a chance to mention in this talk. It's very strange that you think we really mess up with this well, right? With all this bedding plan, vertical fault reactivation, the performance of this well actually beat the type curve. So it's actually performed slightly better than the surrounding regular wells. So I think especially connecting these vertical faults, actually help the production in some sense. And maybe that's even what the Alexis comments are. If we do create a tensor motion of this bedding plan, if we even maybe God bless, I even have Prof go into this bedding plan and keep it open, that actually create also a really large fracture surface over time. So it's funny that its actual production is not bad for this vertical well. But what I also argue, especially in the later stage, what you find is that you don't really create a tensor fracture anymore, and also you are connecting the entire wellbore through this highly conductive bedding plan. So that basically means that you don't really need a very intensive, 20 feet cluster spacing and the 200 feet clay stage length anymore. You can probably frac this well with 100 feet cluster spacing and a 2,000 feet stage length and get exactly the same production results. So that's actually can give you a better economic, if you honoring the fracture system locally. So I would say that actually gave us a good opportunity to enhance the economic, not really from the enhanced production or point of view, but more from optimized completion designs based on your geology feature point of view.
And then Yegor, as you said, has his hands up and will reward his patience by giving him the last
word. Of course.
Thank you, John. Thank you. And so thank you for an excellent presentation. So I really appreciate you giving the talk. And sorry I have to ask like this. I'm on the phone, so I'm not Gen Z, right? So I cannot type quickly on the phone. So anyway, so the first thing I want to do is to kind of reiterate what's because there are kind of similar questions from geomechanics people, and I think I emailed you about it also as well a few months ago. Is that a cool thing would be to know the slip direction, right? And so and the orientation of the fault and the relationship to all the stresses. And as you can see, all the kind of geomechanics people are asking kind of about this stuff. But my question is the following. So I remember a couple of years ago, so you were presenting about measuring fracture velocity, right? So basically, you're doing this, the distance between the peaks of the harsh edge signal, and then you interpret the fracture velocity. So the first question is, where is it? I mean, so why don't we see it in projects right now? I mean, is there like a bottleneck or something? And the second part is, have you tried to apply it for bedding plane slip just to see what's the actual velocity of this bedding plane slip, or maybe you can interpret it as a curvature or something.
Yeah, those are very excellent. So for the velocity, actually, we're now more, at least in my group, we're switching more to the volume of the result of the fracture. We're more switch. Yeah, I'm having some echo, so can Dr. Peter Wang mute? Okay, now we're good. Thank you. So yeah, so on the because the velocity is something that always changing. We know it propagates very fast in the beginning and then kind of slow down as it hit the magnet well. So if you just have the timing of the fracture hit, then I think a lot of times let's go back to here. The volume is a more representative attributes to better describe the fracture propagation speed or efficiency. But we do measure the fracture propagation speed. Actually, we just it's under revision right now. It's under review right now. So we just published a paper that we can use this harsh-shape signal and how fast it's merging towards the fracture hit point. You can use this slope to estimate the in situ fracture propagation at the monitor well location. So that's actually a more direct measurement of the fracture propagation speed, more in situ. So it's not the average speed from the injector to your well, but it's actually just happening very close to the monitor well. So in that case, we also find a couple interesting observations that is related to the fracture efficiency. Because remember, the fracture propagation speed in a certain reservoir is not only dependent on the elastic property or aelastic property of that rock. It's actually a lot of times it's more dependent on your injection rate and also where those injected volume propagate. Is that actually more toward the direction of the fiber or more reverse the direction of the fiber? So in the paper that we're about to publish very soon, hopefully, is what we see is that if you have a parent well on the other side, the fracture will basically propagate very slow towards your fiber well. However, if you don't have a parent well on the other side, the fracture will propagate much faster, simply because it will have more energy to propagate the fracture towards that direction. So I don't think we have a very good, in terms of the commercial science or operational science, we haven't have a perfect metric to describe the efficiency of using the speed. But I think we're approaching, we're trying to get there.
Okay, well, I think you've satisfied everyone.
Okay, that's great.
That rarely happens.
Okay.
Anyways, thank you for such a tremendous talk, and really appreciate the talk and the attendance of everyone. Thanks a lot.
Thank you all. Yeah, fascinating discussion.